Welcome to Volume the Disk method. You've already learned that area is only one of the many applications of the definite integral. Another important application is its use in finding the volume of a three-dimensional solid. In this section, you will study a particular type of three-dimensional solid, one whose cross-sections are similar. Solids of revolution are used commonly in engineering and manufacturing. Some examples are axles, funnels, pills, bottles, and pistons. In this particular lesson, we're going to be looking at objects that are more similar to the pills or the, this one here, I don't know what this is, axle. The axle rather than the funnel or the bottle, because the funnel and the bottle are hollow, they have holes in them, and they're actually calculated a little different way. All right, so these are all solid objects that are created by revolving something around an axis. So if a region in a plane is revolved about a line, the resulting solid is a solid of revolution, and the line is called the axis of revolution. The simplest solid is a disk, a rectangle revolved about an axis. That's why it's called the disk method, because we can represent our volume with lots and lots of disks. All right, so to find the volume, we're going to split the volume into disks of a small thickness and then sum the volumes of the disks by integration. And this is actually using Cavaliere's principle. And he showed that two objects, if they have the same base area and the same height, have the exact same volume, even if the objects look very different. We're going to calculate the volume by integrating area. And the area that we're going to have is a very specific kind of area. So the volume of a disk, so if you think about a disk, it's a circle, right? And this is a disk that has thickness. It's just its thickness is approaching zero. It's infinitely thin, right? That's why there's infinitely many of them. So remember, if we have something that's infinitely thin and we're finding the limit of infinitely many of them, we're using the integral, right? The integral is what gives us those totals, right? We started off approximating with the Riemann sum. We learned how to do them with limits, and then we learned how to integrate numerically, right? So we're going to have the radius times pi r squared, right? That's because our shapes here, they're circles, right? And the area of a circle, right, is pi r squared. The radius is the value of the function, y or f of x, right? So we have pi, we have our radius, which is the value of the function, and we're going to square it. And then the thickness is the analog of the base of the rectangle and the computation of the area under the curve. In other words, it's that little tiny change in x, or dx. Now it's possible that we're revolving around, instead of a horizontal line, a vertical line. So instead of dx, we'll have dy. We'll look at both of those. So the volume of a disk, well, the area of the disk would be pi r squared. Right? The radius is the value of the function, so we're going to square the value of the function. If we integrate that, we get the volume. So this dv here, that's the area. When we integrate and evaluate, we get the volume. So to calculate the volume between x equals a and x equals b, we integrate over the area. So we're integrating area to get volume. We're taking the area, we're finding the area under the area curve, if you will. Right? We're integrating the area curve. Right? And so our dv here, right, that is the derivative, right? We integrate the derivative, right, to get the volume, and that derivative is the area, and the area is pi r squared, with our r being the value of the function. Okay? And usually we factor out that pi just to make it a little easier on ourselves, and then we just distribute the pi later. Let's take a look at some problems. All right, and we'll take a look at our a few important things. I don't know if you noticed, my writing looks like it's going up and down a wave. I think it's still legible, so I won't worry about erasing it. All right, so when we solve these, we're going to sketch the bounded region and the line of revolution. Make sure an edge of the region is on the line of revolution. If an edge of the region is not on the line of revolution, this is not a disk at all. It's actually a washer. That's the next lesson. If the line of revolution is horizontal, the equations must be in y equals form. And it's going to be dx. So for instance, y equals 2x plus 4, it would be a dx, and we'd be revolving around a horizontal line. If we're revolving around a vertical line, we'd have to rewrite it. So if our equation was y equals, if we're revolving around a horizontal line, maybe our equation is y equals 2x plus 4. Right? And that would be a dx. If instead we're revolving around a vertical line, we're going to have to solve for x. So now we have x equals 1/2 y minus 4, and it would be a dy. We're going to sketch the generic disk, a typical cross-section. That'll make sure if the axis is horizontal, always, it's going to be, for volume, it's going to be pi integrated from a to b, our radius squared, which is the value of our function squared, and then the height, because these are actually little disks, they're teeny weeny little cylinders. The height is dx or dy, depending upon which way we're revolving around. Important, when we use the disk method, there's no hole in the solid. If your solid has a hole, then you're using the wrong method. You don't want the disk method, you want the washer method. All right, so to find the volume of a solid of revolution, so this is important notes here. With the disk method, we're going to use one of the following. Okay? And the most important part is that you set these up correctly. All right, so our volume is going to be pi integrated from a to b, r of x squared dx. When our cross sections are going to be vertical cross sections, we're integrating with respect to x, and our cross sections are perpendicular to a horizontal line. In other words, we're revolving around a horizontal line. If the other way we can have this is our volume is pi from c to d, two other letters, r of y squared dy. And that's if we have a vertical axis of revolution. In other words, we're revolving around a vertical line. We're going to have horizontal cross sections will integrate with respect to y, because our cross section is going to be perpendicular to a vertical line. Right? Those are the only two ways to set these up. And our only shape here is a circle. So you just got to figure out the radius. Right? So here for volumes of revolution, about the x-axis, the cross sections of the solid are all circles. Consider the graph of the function y equals f of x in quadrant 1. So the graph, I was going to try to block it out. I can't do that, but because you can't see me do that. So this is our graph, right? So that's our graph. That's our function there. And when we're revolving it around the axis, it creates a circle, right? And a solid object, right? Our cross sections are circles. There you can see our cross section. Our object is solid. The radius of this cross section goes from the x-axis to it's the height of the function. Right? So the area of the circle is pi r squared. That r is our function, the value of the function squared. Okay? That's all there is to these. And actually, I have these in this part of the lesson. They're all graphed. I think in the later part of the lesson, they're not graphed. All right, so we want to find the volume of the solid of revolution formed by rotating the region bounded by the x-axis and the graph of y equals the square root of x from 0 to 1 about the x-axis. Right? So the function intersects the x-axis, right, at 0. The line x equals 1 intersects the x-axis. So our function here does touch the x-axis. Since it touches the axis of revolution, this is going to be a disk, not a washer. There's no hole. And then if we rotate it, you get that lovely picture over there. All right, so now we know what our heights are, right? So I like to draw a little circle in, even if it's not a great circle, just to kind of represent our cross section. There's our cross section. Right? The radius is from the x-axis, there you go, to the height of the function. Right? So our radius is the square root of x. Right? That's our radius. Right? So area, of course, is pi r squared. If we integrate area, and I like to pull the pi out right from the start, we'll get our volume. Right? So remember, area of a circle is pi r squared. So we have the pi already. The r is the square root of x. We have to square it, right? Our radius squared. Right? And this is a dx, because our line of revolution here is a horizontal line. And now we're evaluating that from 0 to 1. At this point, all you got to do is integrate it and evaluate it. Right? I want to rewrite that as x to the 1/2. Actually, you know what? I don't even know why I bothered to say that, because the square and square root are going to cancel. I would have written it as x to the 1/2 had it not had a square on it. The square and the square root will cancel. Sorry, just had a moment there. I'm just so used to rewriting them, forgot to look at what I was looking at. So when we simplify that, that's just x dx. That's a pretty simple integration. So our volume is going to be pi times x squared divided by 2. And we're going to evaluate that from 0 to 1. Right, so I'll leave the pi here, and we'll plug in. Come on. We have 1 squared divided by 2 minus 0 squared divided by 2. That's going to give us 1/2, right, because it's 1/2 minus 0. And our volume, therefore, is 1/2 pi. And there we go. We have found the volume. That's our first one using the disk method. Right? So we're using the fact that our figure is made up of an infinite number of these skinny little disks, the cylinders, right? And the height of these cylinders is dx, right? It's a change in x. And the base area is found by taking the radius, squaring it, multiplying by pi. That's all there is to it. Now the equations might get more complicated, but that's all. The steps are the same. Right? So we want to find, here I have to graph this one. There's the three-dimensional picture. I happen to find it. When I draw it, my pictures don't look quite so pretty, but I do always draw them out. We want to find the volume of the solid of revolution formed by rotating the region bound by the x-axis and the graph of y equals 4 from 1 to 2. Well, I don't really need to put it over here at 0, right, since we're going from 1 to 2. Right, so at 1, 1 to the 4th is 1. It looks just like a parabola, right? If I continued it over here, right, it would go to 0. But that part's not really important because it only goes from 1 to 2. And this one here, we're going from 1 to 2. It is bound by these lines here, bounded by the x-axis and the graph of y equals x to the 4th. This particular one, right, it's this part here. This is what we're resolving, this area under the curve. right? So there's no, and we're right up against the curve. So it's, even though the function doesn't intersect our axis of revolution, right? It's this area under the curve that's being revolved. So that is a solid region. I don't know what this thing's supposed to look like. Maybe like a stand for like a tree or something. You can see it over there, but it's not a funnel. It's not hollow, right? It's solid, right? I don't know what this is, but it's a solid something or other. All right, so now here is, because it's revolving around, right? So sometimes I like to do this. I like to draw its mirror image. It's kind of like dotted lines, because it would be over, especially if I don't have a nice picture like that, because the rest of it would be over here, right? Because you're revolving this thing around. Here is our, I'll draw it this way. There's our radius. Our radius is formed by rotating that function around. Okay? So that would, our radius here is x to the 4th. Okay? So now, remember, our area is pi r squared. So now we just have to integrate that area and we'll get our volume. It's a horizontal axis, so that we're revolving around, so it's a dx. Right? So our volume, we just integrate the area, is equal to pi times the integral, and this is from 1 to 2. Okay, it's the x values because we're integrating with respect to x. And that's x to the 4th squared dx. So we'll take care of the squaring. You always do that first, and then you can integrate, and then you can evaluate. So pi from the integral from 1 to 2, x to the 8th dx, and now we'll just integrate. So our volume is x to the 9th, oops, I almost lost my pi. X to the 9th divided by 9 from 1 to 2. Okay. And so now I'll leave the pi over there. We have 2 to the 9th divided by, that looks like 29. 2 to the 9th divided by 9 minus 1 to the 9th. That looks like 19 divided by 9, but you know that's an exponent. My exponent's looking a little large. And my calculator is over there. Let's see. Well, I know 2 to the 8th is 256. So 2 to the 9th actually be 512, so I didn't really need it. I should probably just double check myself since I went and grabbed the calculator. I think I might need it, though, for a later problem. Oops. Yeah, 512. All right, so this would be, our volume is pi 512 ninths minus 1 ninth. So our volume is 511 pi ninths. There we go. That's all there is. Let's look at a little bit more complicated, at least in terms of, well, actually the figure's pretty complicated. Look at that interesting thing. So, I don't know, it's kind of like maybe a light, maybe they have like a globe and a light, or a crystal. It kind of looks like a crystal maybe hanging from a chandelier. So this is the function 1 plus sine x cubed, actually it'd be x times 1 plus sine x cubed, that's being revolved around this horizontal axis here. You can see it touches the x-axis and intersects in a lot of places. And is creating that shape over there, right? So the rest of the shape, well, if I wanted to draw it in, I hope I don't use up too much board space though, would kind of look like that. Right? That would be the rest of it. And we can continue drawing it. I think that's good enough. So here's going to be our discs, right? They go, and the radius goes from the x-axis where we're revolving to our function, right? So our r here is x times the square root of 1 plus sine x cubed, right? Now, when you see that under the integral, you might go, I don't know what to do. just simplify it out and see. It probably is going to get better because that square. The square is actually going to make things a lot better. So our volume is going to be pi times the integral from, all right, so now we're evaluating that. Oh, this is called a typo. There's no x to the fourth here. I think that's a cut and paste, and I didn't remember to get rid of that thing. X to the fourth was the last function, not this one. And so those are x values right there. So we're evaluating it from 0 to the cube root of 9 pi. All right, so interesting number we have here. I'm going to get rid of these because I think I'm going to need to write right through there. I'll leave that one there that has our sample little disk there. I always want to draw that. So remember our area is pi r squared. Right? We got the pi. We need the r squared. So that's going to be x times the square root of 1 plus sine x cubed. That's squared. And then dx. And actually, if this were not being squared, we'd have a problem. But because it's being squared, things will get better. All right, so now we have pi. I have my square in there. So the square and square root are going to cancel, right? And then, I'm finished writing that. There you go. The x is just going to become x squared, right? You just distribute, it's a product, so you distribute exponents to a product, not sum or difference, but a product or a quotient. And so this is just x squared. And then this now becomes times 1 plus sine x cubed. Okay? Now, there's no way to integrate a product and the way it is. However, we could distribute that x squared, and that will make it better. Or actually, I don't even think it matters whether or not we distribute it. We could. No, we're going to have to. Yeah. No, sorry. I had to think for a moment. Yeah, we need to distribute it because if I want to use a u substitution, I can't use the 1. There's just no absolute way to use the 1 plus sine x cubed. Well, if we distribute the x squared, then we've got x squared. That's okay. If we don't distribute the x squared, we've got 1 plus sine x cubed. Right? What the heck is it going to be with it over here? We can't deal with the product. If we distribute, however, we can use the u substitution and make u be x cubed, and then everything is fine. Right? We can't deal with the product. There's no undo a product rule. And sometimes if everything inside the parentheses is u, that's all good. But here it's not. We only want u. We don't want u to be 1 plus sine because then I need a derivative for sine. The 1's not a problem, but the sine is. But if we just make the u x cubed, all will be super good. Right? So I'm going to distribute. Volume is pi 0 cube root of 9 pi. So now this would be x squared plus, and actually I'm going to write it as two separates because only one of them needs a substitution. Dx plus, and all of this is times pi, x squared sine x cubed dx. I got a feeling I'm enlarging the board. I'm running out of space already. Close my parentheses. There we go. All right, so, and actually, well, my dx should be inside the parentheses. Now let's do a u to u substitution, and we'll change the limits as well so we don't have to substitute those back in, or substitute our function back. And then all of that's times pi. There we go. All right, so u to u substitution on, I'll write it over here. So if u is x cubed, du dx is 3x squared. Just move that over. 1/3 du is x squared. So on the second one there, on the second part of this, we're going to have a u to u substitution. And actually, I put 2 dx's. Let's put 2 integrals too. And then I need to do this. All right, so we're going to do a u to u substitution on that second part, and then all will be just fine, right? Then we can integrate. Absolutely need a u to u substitution here. I'm going to extend the page a little bit because I'm going to start to run out of space. All right, so we have our u to u substitution that we're going to do. Let's change those limits while we're at it. All right, so we've got 0, which is fine. So if x is 0, then u is 0 cubed, which is still 0. If x is the cube root of 9 pi, u is the cube root of 9 pi cubed, which is 9 pi. Right, so that'll be fine. All right, so let's do the substitution. So we have our volume is pi. Now this one not going to do anything with. So from 0 to cube root of 9 pi x squared dx plus, now over here we have 1/3. Integral is from 0 to 9 pi, and it's going to be sine u du. So now we'll integrate. It's a reasonably simple integration now. All right, so our volume is pi, and this would be x cubed divided by 3. That gets evaluated from the cube root of 9 pi to 0. And then plus, I didn't really want to plug that back in, or substitute back again. We had 1/3. Actually, what I didn't want to do is substitute back again. We have 1/3, and this is going to be, so whose derivative is sine? Well, cosine, except it should be negative. Right? Cosine is negative sine u. So this is going to be negative 1/3 cosine u, and that is from, I don't know if I can, I'll just keep going down. I'm trying to think if I had enough room to go to the left or to the right there. I don't think I do. All right, so now we'll just plug in all our values. Pi, so this would be the cube root of 9 pi and divided by 3. And then we've got to plug in the 0 minus 0 cubed divided by 3 plus, and I'll distribute the 1/3 because I already got to distribute the pi. I want to make sure I can keep track of everybody. Oops. And I need another bracket because that's all by pi. Negative 1/3 cosine 9 pi, and then I'll be minus a negative. That's going to make it a plus 1/3 cosine 0. Everybody looks good. All right, so cube and cube root cancel. So this, and now that would be 9 pi divided by 3. So that's 3 pi. So our volume is pi times 3 pi. That's minus 0, so that's not too important. And then plus, we have, all right, so negative 1/3 cosine 9 pi. So you go around the circle 4 times, and you end up at pi. And cosine is negative 1 there. So this is all looking pretty good now. And then we have plus, and that would be 1/3 cosine 0, which is going to be 1. So 1/3 times 1. Now let's just clean this up. So this is going to, our volume is going to be pi times 3 pi. And then we have plus 1/3 and plus 1/3. So that's going to be plus 2/3. So our volume finally is 3 pi squared plus 2/3 pi. And with a unique shape like that, it deserves a unique volume. That's about as complicated, really. Well, that's pretty much as complicated as it gets. Well, we could rotate it on something that's not the x-axis. And then we have to we have to remember that we're not subtracting 0 anymore. We have to subtract that out. But you'll see those problems in the next half of this lesson, because I think that's the last one before, yep, this picks up on the next tape. All right, so thanks for watching, and if you have any questions, just let me know. Thanks for watching Volume of Revolution Disk Method. Bye for now.